Bismillahirrahmanirrahim. Lecture number 8A, Entropy and the second law of thermodynamics. Previously, we have been doing like two different laws of thermodynamics. One was the zeroth law of thermodynamics. We were talking about the thermal equilibrium in it, and we were defining thermal equilibrium with the property called as temperature. In the first law of thermodynamics, we were talking about the conservation of energy, and we did define those conservation of energy with different properties, or if I would say like enthalpy, entropy, enthalpy and internal energy. Today we'll be talking about the second law of thermodynamics, and for the second law of thermodynamics, we would be defining that law with the help of the property. But before we go to the second law of thermodynamics, let's define or let's think why we need second law of thermodynamics itself. Uh, let's have an example. Like example, we have got unrestrained expansion. We have got a steam. Let's say we have got a steam inside a container, and one side of the container is totally vacuum. If you break the membrane, let's say the steam will pass from one direction, and it will actually occupy the vacuum side of it as well. And what actually would happen, all of the container would having the steam, and with a different, obviously with a different pressure, but the volume would be changed. uh, and obviously there's another example of the heat flow from, let's say, body A, and let's towards the body B. Let's say like body A is having a high temperature, and body B is having a low temperature. And so obviously the temperature will, or the heat will flow from the high temperature to the low temperature, and once we have got the thermal equilibrium, there won't be any heat transfer from the system. Then let's say, in the same manner, if we assume like, or if we say like, whether this thing would happen or not, what I mean to say, like whether the steam whether the process which actually will occur from this direction to this direction, will it occur in this direction to this direction naturally or not? Or in other words, if I'm saying like there was actually the thermal equilibrium from high temperature reservoir to a low temperature reservoir, and we were saying like heat was flowing from this direction to this direction, and there was a thermal equilibrium, but whether it will actually happen to in this direction or not, these both processes, unfamiliar though they may be, are compatible with the first law of thermodynamics. But in other words, the first law does not prohibit their occurrence. In other words, what I'm saying, like there must be some great principle that describe the direction of a natural process, which tell us like which first law would be happening or which first law would not be happening. So the first law of thermodynamics, sorry, the second law of thermodynamics, we would be talking about this great principle, or we would be talking about the principle of the, in second law of thermodynamics, we would be talking about the principle of the direction of a natural process. What, why the natural process would flow from one direction to another direction, and why it will not flow from the other direction. Before we go to the formal definition of the second law of thermodynamics, let's define a property, and that property would help us in defining the second law of thermodynamics. And the property is called as the entropy. The entropy is the degree of randomness, disorderedness, and uncertainty of energy in a system on a microscopic level. So it is the randomness, disorderedness, and uncertainty of the energy in a system. So that means like if we have got a low entropy, that means like we would be having a high energy, and if we have got a high energy, we would be talking about the low entropy. So let's have an example first, and then we will be able to understand fully what entropy would mean. Let's have a look. Let's have an example, and let's have a look to the, have got some marbles in our hand, or let's say we have got some balls in our hand, and those marbles or those balls are actually compact enough. Let's say these balls are having tightly packed, and say let's say we throw those marbles, we throw those balls on a thick mirror somewhere, and let's assume like when you're throwing those marbles, these are not scattered. So the marbles actually you're throwing from this direction will go passing from these paths, and let's say it will hit the mirror over here. So what would happen actually? So naturally the mirror will shatter. Or the same marbles, let's have the same number of marbles, same number of balls in your hand, but when you are throwing it towards the mirror actually, during the transfer or during the traveling actually, these marbles scattered, or it's a, like the marble would go in this direction, the marble would go in this direction, or in the other word it will not actually hit the mirror in one in a hole, I would say. So some of the marble will hit the mirror, some of the marble will not hit the mirror. So what would happen? Most probably the mirror will not break. It will have some cracks. You might think like it will have some crack. Some of the small marble will hit the mirror, some of them will not hit properly, some of them will scatter somewhere. So what actually has been changed? Hitting the marble, or you were hitting a mirror, but all the marble having the energy with them were hitting the mirror as a whole, or it's a like more ordered form or more non-random form. It when it will hit the mirror, actually it shattered. But now what actually happened in a second example? Now the balls or the marbles, they are now the disordered now, they are now randomized now. So now what actually happened now? So the energy is now disordered, the energy is now randomized, this the energy is now scattered. So that mean like the entropy, the first they were having in a first condition, they were having the low entropy, low orderness, low randomness, but having a high energy. Now, in other conditions, when you were moving from the low randomness and low orderness, you were going for the scattered one. Now we have got the high randomness, we have got the high disorderness, and we are having the high entropy, but now we have got the low energy. So now we are saying like we are going from the high ordered form of energy toward the less ordered form of energy. Or what we are saying like we are going from the less entropy towards the high entropy, or high energy towards the low energy. So now what actually the entropy is? It is the degree of randomness, disorderedness, and uncertainty of energy. So, more the randomness increases, sorry, so more the randomness increases, more the entropy increases. More the disorderedness increases, more the entropy is increases. More the uncertainty is increases, more the entropy is increases. So you might think like entropy in terms of orderness, in term orderness in an isolated system. So that means like low entropy would mean like high ordered compact form of energy. And that means like high entropy would mean like low ordered and actually scattered form of energy. The direction of the process or change in a state as specified by the change in entropy is tied to the direction of heat transfer. For example, you are burning the gasoline, let's say gasoline, and that gasoline is in a form of, let's say, liquid. When you are actually burning it up, it actually go into gaseous form, or if I would say like burn it out. So that means like when you are going from the high energy towards the low energy, you are actually releasing some amount of heat as well. So that means like the entropy change is also associated with the direction of the heat transfer. So when you are actually changing the entropy, there is also some heat transfer as well. So that means like both of them are tied together. You can take an example of gasoline. You can take an example of cooking the food. You can take example of sunlight. So these are all actually the entropy. And that entropy is tied towards the direction of the heat transfer. So now let's define the second law of thermodynamics. As we define the term entropy, now let's define the second law of thermodynamics. Entropy in an isolated system that is not in equilibrium will tend to increase over time until it reach maximum equilibrium level. So let's focus on different terms in it. So we have got the entropy, which will be an entropy of an isolated system. So that means like we are not getting any energy in and out of the system, energy and mass in and out of the system. So we have got the entropy of an isolated system. Initially, that entropy is in equilibrium. So that means like when we have not in equilibrium, sorry. So entropy when we are having in a non-equilibrium process, it will increase over time once it reach the maximum equilibrium level. Yes. So we have got initially we were having a energy, if I would say like high energy, and that was actually in a form of temperature over here. So and that but that energy was not in equilibrium. So entropy initially in a non-equilibrium process was minimum. Now what happened like once you open the wall, it tend to increase, the entropy tend to increase over time. It start flowing the heat flow or the molecule flow from this direction to this direction, and it actually is changing from non-equilibrium towards equilibrium. It is changing from more, I would say like order form towards the more random form, the most order to a disorder form, the most low entropy towards the high entropy. Once you reach the equilibrium level, once you reach there, you would be having a maximum equilibrium level and you would attain the maximum entropy. So if you keep the door open between the two rooms of different temperature, the cooler room will become warmer and the warmer room will become cool down until it reach same temperature, or in other words the same equilibrium level. So an isolated system being initially in a non-equilibrium state, so initially it was in a non-equilibrium state, will evolve from the macro partition with low prob multiplicity. Let's leave that one. So it will evolve from the low entropy towards the high entropy. So it will go from the low entropy towards the high entropy. Once the system reach the high entropy or the highest entropy, and the highest entropy is at the maximum equilibrium level. So when it reach there, it will stay there. So now if you say like what would happen next actually. So yes, if you provide with another non-equilibrium condition, let's say body having both of them is having the same temperature and this is having a low temperature, so obviously there will be another non-equilibrium in a system and the heat will again flow from this direction to this direction and so on and so forth. So that means like you have to just attain the maximum equilibrium level rather than actually just we are saying like the equilibrium itself. So the isolated system initially, when it is actually at a low entropy, non-equilibrium, will try to reach towards the high entropy, and once it reaches the highest entropy, it will stay there. Now the formal definition of second law of thermodynamics. The entropy of an isolated system never decreases. That means like entropy of an isolated system, whether it will increase over time or whether it will stay there. That means like increasing over time would mean like when the system is in equilibrium, and stay there mean like when the system reach towards the maximum equilibrium level. There is no condition in which it will decrease from the its final state. Although we cannot calculate entropy, we can still measure the entropy, and that's what actually we call it as a Clausius statement. ds is equal to dq by t, or or du by t would be actually the entropy. Remember, if you remember, internal energy was also the was also known as the randomness and disorderness of the molecules. So you can imagine like the randomness and disorderness in a system is also the entropy as well. Um, if you're talking about equality sign, as I said, like, so equality would mean like, if I'm saying like dq by t, equality mean like we are talking about the equilibrium level. And yes, we are talking about the equilibrium, or we are talking about the quasi-equilibrium process. Quasi-equilibrium process, previously we did define a little bit, we call it as a reversible, but today we will be more discussing it in terms of entropy changing and and in a form of second of thermodynamics. So this is the thermodynamic definition of entropy, which actually the Clausius introduced in 1894. You can go with the example. So now, what is actually a reversible process? A reversible change are conceived to be those that would occur very slowly. We call it as a quasi-static process, giving all the molecule in a system time to adjust to a new condition, and all state variables time to adjust while still remaining uniform throughout the system. So what we are saying, like, we are moving, or we are actually the process is moving in such a slow pace, or if I would say like it is actually going in a quasi equilibrium process, that we have got sufficient time that the system is adjusting to a new condition, and the it is remaining uniform throughout the system. Theoretically, what we are saying, like, we are stopping at any small point and reversing the change. You remember, like we were saying, like plus minus dp over here, and p plus minus dp, and we were saying like this dp change in the pressure was so small that it was mostly negligible. So that's what we are saying, like theoretically you can imagine like we are actually changing so slowly, and yes, we are reversing the change back to the initial state. So recovering the previous thermodynamic state. So by Fermi, the transformation is said to be a reversible transformation when the successive state of transformation differ by infinitesimal from the from the equilibrium state. So in other words, what we did said, like, this change was so small that it from the equilibrium state actually it differ very so small. So the transformation is said to be reversible when the successive state of transformation differ by infinitesimal from the equilibrium state. In other words, when there is no entropy change. That means like entropy is randomization, disorganization, and uncertainty of energy. So that means like when you are talking about non-randomization, non-disorderness, so you are talking about the entropy which would remain constant. So you are what we are saying, like you are giving the system time to adjust to a new condition. So a transformation is said to be reversible when the successive state of transformation differ by infinitesimal from the equilibrium state. In other words, we would be talking about the reversible process when we are talking about the entropy change equal to zero, when there is no entropy change in it. So that defines the irreversible process now as well. So irreversible process would be the process in which the entropy, there is an entropy change. There is some randomness in a system when there is a disorganization in a system, when there is uncertainty of energy in a system. So we would be talking about like there is actually entropy created. So the process in which the new entropy is created is called as irreversible process. The system spontaneously change on energy is transferred in such a way that it creates new entropy that does that does not allow complete recovery of the all aspect of previous thermodynamic state. That means like the entropy at final would be more than entropy of the initial. So going back to the our definition, entropy of an isolated system, entropy of an isolated system, whether it will be increases or it will remain constant. So that means like ds would be equal to zero when we are talking about the reversible process, and ds would be greater than zero when we are talking about the irreversible process. So the criteria to the whether the process is completely reversed must be based on the initial and final state of the entropy in the form in the form present above. The second law furnishes a relation between the property defining the two state, thereby showing whether a natural process connecting the state is possible or not. Whether if the entropy, if I'm saying like if the entropy is not changing, so we would be saying like the system is not moving and it is actually in an equilibrium condition. And if the entropy is increasing, then that means like the system would be actually moving forward. And if we are saying like the entropy is decreasing, then naturally this does not occur and it is impossible.